welcome back. I hope that you all had a good holiday and a little bit of a break. A lot of you are there. You've got the model figured out, and these problems are starting to be boring to you. And yet there are others of us in this room who are just on the verge. You know, it's just about to click, and maybe part of it clicks, but maybe voltage is still a mystery. Hopefully, in today's lecture, we'll make it click for those of you that are still struggling. Now, on Tuesday, we're going to have an optional lecture. I'm just going to go over problems one after another. And if you've got it figured out, you don't need to come. There won't be any clicker questions. There's no reading quiz for that day. So if you still need help after that, I'm going to have a review session Tuesday night. Not tonight. Originally, it was scheduled for tonight, but it's going to be better Tuesday night after we've had all of the classes and the reviews. And so that'll be in this room Tuesday evening at 7 o'clock. Questions about the plan? The exam then opens the next day on Wednesday and closes Friday. And we'll be over at the testing center. Now, I was concerned that a large number of students came to my office saying, after that last exam, I thought I understood it. I thought I had electric fields and forces down, and then the test didn't go my way. I don't know what happened. And so what I've done this time is I've created an online exam. And that online exam you can find at Max if you just go, let me get into student view. If you just go to the upcoming week, there's a link right there, sample exam 2, test your preparation for midterm 2. Okay. And there, under instructions, I've written this note. This practice exam will not affect your grade in any way, but it is a test. You will only be allowed to take this test once, and after you take it, you will receive your score, but not the correct answers. The purpose of this exam is not to teach you about circuits. That's the homework. That's the 2 sample paper exams, all of the tutorials. That's to help you learn. The purpose of this exam is not to teach you about circuits, but rather to measure what you have already learned about circuits. After you take this exam, you will know whether you can go skiing with your friends or whether you should go back to studying. Okay? This is purely to give you an idea of what you're going to get when you take the real exam. If you get an 80% on this online exam, unless you do something over the weekend, you're going to get 80% on that exam that you take at the testing center. Okay? Questions on that? And there's no deadline. I mean, it says that it's due tomorrow night, but you get full credit, which is 0. But it's scored out of 120 points. It just won't affect your grade at all. But you won't be counted late after the deadline. I just wanted it to be somewhere where you would see it, and that was an empty space on Friday there. Okay, let's start with a prayer. Hannah, would you offer us an opening prayer today? Thank you.
Father in heaven, we're so grateful for this day, grateful for the chance we have to be here to visit Francis and his efforts in preparing for this lecture. We pray that I would like to take time to review the concepts we've already learned, that our minds and our hearts will be open to the spirit to learn and apply some understanding at a deeper level. You'll be able to walk away feeling more confident in the abilities that Dr. Francis is helping us develop, and we may be able to use this knowledge to become more like the Savior, that we may be able to find ways to live and love those around us. We're grateful for this opportunity to gain education, and we love you and say these things in the name of Jesus Christ. Amen.
Amen. Thank you. Okay, so. Questions about the exam? This is a question off of one of your sample exams, the paper exam. And how many, just by show of hands, are still struggling with these messy circuits that have lots of resistors in them? Okay, so I'd like to go through this problem as an example of those problems. And you'll see that they are solved the same way. So let me start by going to that show up? Okay, now the first question I always get when people are working with this problem is I went to the key, and the key said that these 3 batteries could be replaced by one battery that was 240 volts. And the question is, how do you get 240 out of 200 and 160? That looks like 360 to me. Anyone see a problem? Yes, sir.
Batteries backwards, so it's 300 minus 60.
Yeah, that 60 is pointing backwards, fighting the other 2. And so what I have is these 2 add together, the 200 and the 100, they act as if they were a 300 volt battery. But then the 60 is pushing the other way, so I have to subtract it, and that's where I get the 240. Okay, so be observant. It's always the long line that is the positive terminal of the battery. Now, when I work these problems, I always ask the same 2 questions over and over again, and that is, what's in series, what's in parallel? So let me draw this circuit up here. I'm going to leave off the ohms, okay, just to save some okay. The first question I ask is, what's in series? Well, these are in series. Everything that goes through the 30 has to go through the 60, and everything that goes through the 60 had to have come from the 30. There's only one path. Also, these 2 are in series. Everything, if Fred went through the 90, Fred has to go through the 50, okay? And if Fred went through the 50, he had to have gone through the 90. Does that make sense? And so then I asked the second question, and that is, what's in parallel? Oh, what else is in series? Anyone see another thing? Yeah, the 20 and the 40. Okay. Okay. And then, I ask, well, let's just redraw that. Okay, that's probably enough to go on. So I'll do it down here. 90 and 50 is gonna be 140. And then I've got 60, 60, and 60. And then here, I've got 90. And then 105 and 210. Now, the next question I ask is, what's parallel? When things are parallel, they have direct connections with nothing but wire on both sides. So these guys are all parallel. And the 105 and the 210 are parallel. Okay? And so I would circle this, and I would circle that. And then I would redraw the circuit again. You should have a lot of scratch paper when you go into your exam, because you're gonna have at least one of these problems, okay? So now I've got my 240 volts. And the 260, I'm sorry, the 360s look like a 20. Don't they? Okay, and so that's gonna be 140 and 20. And then here, I've got 90. And let's talk about this 105 and 210. How do I deal with that? Well, I look for the common denominator between those. And the common denominator between those is 210. I can make all of those out of 210s. The one on the right, obviously, I just need one 210. But the one on the left, I'm gonna need two 210s. Two paths are twice as easy as one path if they're identical paths. And so two of these 210s is gonna give me a 105, right? So now I have 1, 2, 3 paths that are all identical. I use my rule, which says you take the resistance of one path and you divide by the number of paths, and that gives you the resistance of the network, which would be 70. So this is going to look like 70. And then I ask the same questions again. What's in series? Well, this is in series and that's in series. So now it looks like 160 and 160. Whoops, spell it right. And then I ask what's in parallel. Well, obviously these guys. And so the whole circuit boils down to this. One resistor that's 80 ohms and a battery that is 240 volts. Okay. And so if I use, okay, I don't want to yank that off. There's two ways to use Ohm's law. The global method is to say delta V is equal to IR, where the delta V is the voltage of the battery, and the I is the current through the battery. And the R is the equivalent resistance of the whole circuit. Okay, so in this case, I would have 240 volts is equal to the current through the battery times 80 ohms. That gives me the current through the battery is equal to 3 amps. Now, there's another way to use Ohm's law, and that's locally. And that's what we'll do later on in this problem. And that is delta V equals IR. But this is from any point A to any point B. And I use the current that passes from A to B times the resistance that's between A and B. Okay? So if I want to know what the voltage is from A to B in this problem, I need to know how much current actually flows through from A to B. And that means I've got to be the river. I've got to start at the battery and I've got to divide up that 3 amps. Okay, we found that 3 amps was going through the battery. And when it gets here, it splits and doesn't come back together till down here. And if I look at this picture right here, that's what it looks like when the current, I got 3 amps coming in here and it splits here and comes back together there. This whole branch on the left looks like 160 ohms. Everything on the right looks like 160 ohms. So it's going to split 1.5 and 1.5. Okay, so if I go back here, I would send 1.5 amps this way and 1.5 amps that way. Now, when those 1.5 amps get here, it splits 3 ways, 3 equal ways, because each path looks like a 60. And so that's going to get a half amp. And this is going to get a half amp. And this is going to get a half amp. Now, when that 1.5 comes down here, it's going to split, but not 50-50, some other way. This path over here is twice as hard as the path on the left. And so the path on the left, the easy one, is going to get twice as much current. Now, one way to see how to split that is to go back here. I've got 1.5 amps coming down here, and these 3 paths look the same. And so this is going to get a half amp. This is going to get a half amp. And this is going to get a half amp. But then I remember that these 2 paths are really just the easy path, the 105. And so when the 1.5 comes in, I'm going to get a half and a half is going to give me 1 amp. And over here, I would have the half amp. You see that the path that's twice as hard gets half as much current. Okay, is everyone okay with that? Check on your neighbor real quick.
If I added something else, the better thing I added, over you know. Then it would be like. It's not gonna get. Oh, yeah. I added something. You understand it like. Yeah. Everybody's getting a little bit of jobs. Yeah.
Okay,
I think it's everybody gets the same, but that's the one thing.
now. In this problem. We're asked to find the current that passes through that 20 ohm resistor. And we already did that, it's a half amp. We're asked to find the voltage drop from A to B. Well, I can use this local version of Ohm's law, and I just take the current from A to B, which is a half, times the resistance between A and B, which is 40. A half times 40, there's 20 volts from here to here. Okay, so I'm gonna go in and I'm gonna write that in a different color. I've got 20 volts here. Here I would have 10 volts. Here I would have 30 volts. Here I would have 30 volts. What about here? Across that 90, I would have 1.5 amps times 90 ohms would be 135 volts. And down here, 50 times 1.5 is going to be 75 volts. So look here. Any path, I've got 135 times 10, plus 10, plus 20. I'm up to 165. If I add 75 to that, I get 240, the battery voltage. Let's do the other path. I've got 1.5 times 30, that's going to be 45 volts. You'll tell me if I go off the screen, right? And this is 1.5 times 60, that's going to be 90. And this is going to be a half times 210, that's going to be 105 volts. And this is 1 times 105, that's 105. And so then we go back and we say, any path, I've got 45 plus 90, that's 135, plus 105, that's going to be 240. Any path, 240. Okay. Questions on that? Now, even if I don't ask you to find the current through the battery, even if no points are assigned to the current through the battery, that's always the first step. You can't do the rest of the problem without finding the current through the battery and then being the river and splitting it up at each junction, 50-50 or some other way. Okay. We able to go on to another problem? Yes, sir.
Just for question B, just determine the total current through the circuit.
The total current through the circuit would be the current through the battery, or the 3 amps. Yep. Yep. That's the river that we're dividing up. Okay. This problem is also in one of the sample exams, and it's a really great learning problem. It was on an exam about 30 years ago, and it turns out it's not a good exam problem. A lot of people had a lot of difficulty with it. That's how I know it's a good teaching problem. Do I have a helper over here? Look for the helpers. Thank you. Let me take one of those from you. Okay. Okay.
Like, don't write it down.
Raise your hand if you don't have a copy. Thank you. Okay. In this problem, we are using a nichrome wire. Now, you remember that in one of the tutorials, we had a nichrome wire and we decided that it was different from a connecting wire, the types of wire that I've got up there on the board. The connecting wires we assume are ideal. They have zero resistance. But the nichrome wire, the whole point is that it has resistance. It has resistance that's fairly similar to that of a bulb. And the longer the piece of wire, the more resistance that you have. And so in this case, we have a piece of nichrome and we can change the length of it by where we connect our connecting wire to. And we find that as we lengthen the nichrome wire, the voltage across the nichrome wire changes. The voltage across the battery, because it's an ideal battery, doesn't change. It stays 1.5. And so we're asked to predict in this table the voltage across bulb A and the voltage across bulb B and the voltage across bulb C for each of these lengths of nichrome wire. Now, the easiest one, of course, is bulb B, because it's on a path parallel across the battery, so it's independent of everything on the right. Come heck or high water, it's going to have 1.5 volts across it because it has direct connections to both sides of the battery. So I can just write 1.0, you can't see that. Now you can. 1.5 volts, 1.5 volts, 1.5 volts, 1.5 volts. Whoa. And if this were an exam, you just got points for that. Boy, that's easy. Okay, now, what about bulb C? Well, bulb C is parallel to the nichrome, is it not? And parallel paths always, and by that I mean every stinking time, always have the same volts across them. Okay, and so whatever I have across the nichrome, I have across bulb C. Whatever I have across the nichrome, I have across bulb C. Okay. Now, what about A? Well, if I use my voltage model, I know that any path from one side of the battery to the other side of the battery has to drop the same voltage as the battery voltage. So that means that the voltage across A plus the voltage across the nichrome has to equal 1.5 volts. Okay. So if the nichrome has a half volt, the bulb A has 1 volt. If the nichrome has 0.6, this is going to have 0.9. If the nichrome has 0.64, this is going to have 0.86. And if it has 0.67, this is going to be 0.83. These are volts. Check on your neighbor. See if that is obvious to everyone. What's that? Any parallel paths, whether they've got bulk or nichrome or dead fish on them, they've got the same bolts across them, okay? Okay. Now. Imagine my surprise 30 years ago. We didn't have a testing center. I had these huge classes and the exams were given all at once. Everyone had to show up at the same 2-hour period. We had every large room on campus and I was running from room to room to answer questions. And we got to this problem here and I got stopped everywhere I went with the same question. Okay, let's read this here. Suppose that the nichrome wire were made very long, 3 miles in length. Predict the voltage across the wire, the battery, and the 3 bulbs. Can you guess what the question was that they were asking me? How many centimeters in a mile? And I have to assure you, I have no idea. I have no idea. That's just not one of the things that I can remember. I struggle to remember my children's birthdays and grandchildren. That's something Sandra takes care of. Okay. So that clearly can't be an important part of this problem. The answer I gave people was just that, oh, that's a typo. It's not 3 miles. It's 3,000, 3 million, 3 trillion miles long. Okay, very long, very long. Okay. Now, what's the voltage across the battery going to be? Yeah, that's still 1.5 volts for an ideal battery. The voltage across B is still going to be 1.5 volts. Tell your neighbor what the voltage across the nichrome and the voltage across A is going to be.
Are you saying that because the neck wire is so long that there's maybe just migrating around through it? But then that would also mean that I didn't agree with them. Actually, so.
Okay. Just for kicks and giggles, let's go on to part C and come back to part B after we do part C. In part C, we take the nichrome completely out and we leave the gaping hole behind, just nothing but air there, okay? And so there's no nichrome there. The voltage across the battery is 1.5 volts. The voltage across bulb B is going to be 1.5 volts. A and C are now in series. They're going to be equally dim. And the voltage across them has to be the same. Again, because they're in series. And it has to add up to 1.5. So that's going to be 0.75 and 0.75 volts. That seem clear to everyone? Now, let's go back to B. If I look at B and I ask myself, once Fred and his friends go through A, and they have a choice between going through C or 3 trillion miles of nichrome, where are they going to go? C. Oh, I don't speak Spanish, and yet the gift of tongues just helped me. D, you're right. Okay. And so the voltage across A is gonna be 0.75. The voltage across C is gonna be 0.75. And the voltage across the nichrome has to be the same as the voltage across C, which would be 0.75. Now, Greg, whoops, sorry. Greg, you told us that the battery voltage, the oomph of the battery, had to be divided up between the things that were harder to get through. The bigger the resistance, the bigger the share of the oomph. Shouldn't the 3 trillion miles of nichrome get all of the 1.5? Oh, no. That rule is only true for things that are in series. Okay? Things that are in series. And if I look at that circuit diagram again, is A in series with C? No or heck no. Heck no. Everything that goes through A doesn't have to go through C. It has to go through the network of the nichrome and C. Now, you know that parallel networks always have a combined resistance that's less than the least. So that's going to have a resistance that's a little bit less than one single bulb. But if the other path is 3,000 miles of nichrome, it's going to be pretty close to one bulb. If I use that formula, 1 over R equivalent is equal to 1 over the resistance of a bulb plus 1 over the resistance of 3 trillion. I don't even know how many zeros there are. We'll ask Elon. Okay. Miles. Okay. Well, this is such a big number and it's in the basement that I can just forget about. And so the resistance of that combination is pretty much the resistance of a bulb. And so I can think of those two bulbs, A and C, as being virtually in series because the other path was so ugly that it looked like an open gap. Check with your neighbor, see if your neighbor could have gotten this right on an exam if they took this exam.
Okay, it's like thick and hard. I want to think thin and dark for but I don't think it's in a light room. There are pages.
You know what, I just need like. I'm gonna get up on this, like. Yeah.
That's because I understand like the people kind of say like, okay, that's maybe more.
I think the opposite. Like the math, sometimes I can figure it out, but it's, I'm
Like the 405, the one from down that day, I was like, oh yeah. But
I probably I got a great problem, right?
Are there questions? Yes.
Okay, so greater resistance means more voltage in like relative resistance. So like just when things are in series.
I can't hear that. What was the question? Would someone translate for me?
I also don't understand the question.
Yeah.
Okay.
Could you explain the greater share of resistance affecting?
Oh, yeah. If I have 4 ohms and 8 ohms across a 12-volt battery, the 12 volts you can think of as the loop of the battery. And when things are in series, they have to have exactly the same current through them. Whatever is going through one has to be the same current that goes through the other. And so the battery has to shove the same number of coulombs through this easy resistor each second as it does through this hard resistor. And so when it divides up its oomph, it's going to divide it up accordingly. Since this is 1/3 of the total resistance, and this is 2/3 of the total resistance, and they're in series, this is going to get 1/3 of the 12 volts or 4 volts, and this is going to get 2/3 of the 12 volts. You know what? That looks mysterious. Let's make this 24 volts. This is going to get 1/3 of the 24 volts, which would be 8, and this would get 2/3, which would be 12. I did the 24 just because I didn't want this number to be the same as that number. That would never work. Yes, sir.
16 volts, I think it's
16 volts, 16.
Ah, yeah. Thank you. Math is hard.
So for this problem, are we, is it important that you specify that it's nichrome wire or whatever?
Yeah.
Than Normal wire, if it was normal wire, then it's different matter.
Normal wire, I would be shorting out bulb C, and so the answer would be 0, regardless of how long that wire was. It could be the 3 trillion miles and it would still be shorting out.
Great, thank you.
Okay. Let's move on to another problem. And this is another handout, so I'm gonna need the helpers again. Thank you.
But since it is.
Who have I got over here? Thank you.
Oh. There'd still be some stuff.
Okay. I promised you that on your exam, you would have a problem like this. And you notice that in every one of the 2 sample exams on paper, and you'll see on that online exam, in each of those exams, we have a problem like this, where there's a messy circuit and you're asked to compare bulbs 2 at a time. And then we make changes to the circuit. Okay, and we ask, how does that change affect this bulb or that bulb? Now, in those problems, the key is to be the river, and everywhere the current splits, you have to decide, does it split 50-50 or some other way? And that's why I told you that the most important tool in your toolbox is the ability to look at 2 networks and immediately say, oh, that one's harder to get through. That one has more resistance. Being able to do that is the same as being able to draw a free body diagram in 105, okay? That's gotta be something that you're good at before you go to that exam. Now, how do I tell? What do I do to, first of all, tell your neighbor, when the current splits, right there, some going left and some going right, tell your neighbor which one gets more than half and which one gets less than half. Tell your neighbor real quick.
Give me like a tiny fraction. 2.5.
Okay. The way you can tell is you draw both exactly the same. Now, clearly, to get through the right-hand side with only two bulbs, this would be C and this would be F. And if that was the circuit, this would be trivial. It would split 50-50 there and all the bulbs would be the same brightness. Then you get a different color pen and you ask yourself, what's missing? Well, D and E are missing. They are a parallel branch, a parallel network, if you will. But I don't care what they are. I care how they were added. And so the critical point here is, do I need to pick up my eraser to put in D and E? And the answer is yes. I've got to break this line, shutting off these two bulbs, and shove these two in that branch. And so that means that this is going to be the big resistance, and this is going to be the little resistance, so that when the current splits, it's going to split with more than half going this way and less than half going that way. Okay, so now we want to rank the bulbs, and this should be easy. A and C are both indicator bulbs for their respective branches. We'll call this branch 1 and this branch 2. And so since A gets all of the big current and C gets all of the little current, A is going to be brighter than C. If we compare C to D, well, that's an all versus part. I know that the current through C is equal to the current through D plus the current through E. And then when we compare C to F, they are equal, and I can justify that with one word: series. Okay? Now, I can show this by hooking up this circuit. If I hook this circuit up, let me label my bulbs. This be A, B, C, D, E, F. Okay. Now I connect the negative terminal of the battery here, the positive terminal of the battery here, and is that what we predicted? A is brighter than C, and C is the same brightness as F, and these guys are so dim we can't even see them, but we know that they have to have half the current through C. Is that correct? Okay, so we got that right. Well, now we're asked to unscrew bulb D and leave the empty socket behind. Well, before I do that, let's make some predictions. What's going to happen to bulb A? Shout it out. Nothing. It's on an independent parallel across the battery path. Nothing. What about bulb E? Well, let's think about this. If I take out bulb D and leave the empty socket behind, I've changed my circuit. There's 4 ways to change a circuit: add a path, remove a path, clutter a path, declutter a path. Which of those 4 did I do? I removed a path. That's going to increase the resistance of the circuit. That's going to decrease the current through the battery. The current through this side isn't going to change, but the current through that side is going to change. That means C and F are going to get dimmer because they get all the current through that branch. They're going to get dimmer. But with E, I've got a pizza problem with current. It was getting half of the bigger current through branch 2. Now it's getting all of the smaller current through branch 2. So I go to my voltage model and I say the voltage across C plus the voltage across E plus the voltage across F has to equal the 12 volts of the battery. By removing that path, I know that C and F get dimmer. It's a zero-sum game. It's still got to add up to 12. So E has to get brighter. Questions on that? That's how you use the voltage model. That's what we did right there. We just used the voltage model. Okay, now we put D back in and we add a new bulb. Let me draw it for you. We add a new bulb between points 2 and 3. That's going to be the new one. Such that the bulb is in parallel with bulb C. So, what's going to happen to bulb F? Tell your neighbor real quick. What's going to happen to bulb F? Get brighter, dimmer, or stay the same? Okay. Remember, there's 4 ways to change a circuit. In this case, I added a new path, and it doesn't matter what's on that path. It's new. And so that is going to lower the resistance of the circuit, increase the current through the battery. The current through A and B is not going to change. And so that means the current through branch 2 has to increase. Well, all the current through branch 2 goes through F, so F is going to get brighter. What about bulb E? Well, bulb E always gets half the current through bulb F. Has to. And so if F gets brighter, so does E. And so if I go back to the voltage model now, this is still a path from one side of the battery to the other. And I know that if F gets brighter and E gets brighter, C has to get dimmer to add up to 12. Okay. Let's check our predictions. The first prediction said that when I take D out of its socket, I'm going to, we said that C and F would get dimmer and E would get brighter. Did it come true? Yes, it did. Okay, now I put D back in. And now I get myself another bulb. And I'm going to put that, sorry. I'm going to put that from point 2 to right above bulb E. Watch what happens. What did we predict? We said that F would get brighter, E would get brighter, and C would get dimmer, okay? So we hook that up. Whoa. This is now something I can see the glow, whereas before I couldn't see any glow. So this got brighter, that got dimmer. Physics works, people. That's what makes it different than chemistry. Yes,
Would bulb A stay the same?
yes, in all of those situations, A and B stay the same.
When you unscrewed light bulb C, was E brighter than C and F? It kind of looked like it.
Oh. It turns out that they have to be the same. C and F, I went to great pains to take all of the bulbs they had down in the demo room and see which two were the most identical. And so I have colored them on the back so that whenever I need two bulbs in series that look the same, I do those two. Here I ran out of bulbs that were identical. Yeah, but good observation. If these were identical bulbs made in the same factory by the same worker, they'd all be identical, bright or dim. Okay. Now, we turn the page over. We put all the bulbs back in, we take away the new bulb, we go back to the original network or circuit. And this time we add a connecting wire, not a nichrome wire, but a connecting wire from point 1 to point 4. And the question is, what is that going to do to our circuit? What's that going to do to the brightness of these bulbs? Now, let me ask you a first question with your clicker. Yeah, get your clicker out. Now, remember, on Tuesday, there will be no clicker questions. So if you want to stay home and sleep, that is fine. We'll be working sample problems. Does bulb A go out? Yes, no, or I don't know.
If I could say that bulb F is not there, then. Well, you can't get past.
You can, so true. You can,
Why did you say one for one?
yeah.
Two.
Okay, last call. Get your vote in.
Oh, and then you.
Four.
Everyone voted? Oh, we're not sure. We're not sure. Okay, let me ask a different question. Does bulb E go out? Yes, no, or I don't know.
Wire there.
Okay, last call. There's one. Oh, that's us. Again, we do not know. Okay. That is unfortunate. But it does make me feel really, really good about my decision not to open the exam tomorrow. Okay. Because some of us aren't ready. Now, let me remind you of this problem that we did last week. You remember that we could take this connection of a connecting wire and move it anywhere we want without changing the circuit or the brightness of the bulbs. As long as we don't cross an element like a bulb or a switch or a battery or a resistor. Okay, as long as we stay on just connecting wire. And so here we said, oh, it's pretty clear now that B is shorted out. Well, if we do the same thing here, I can move that connection at 1 over to there and it doesn't change the circuit. I can move it over to there, it doesn't change the circuit. I can move this connection at 4 to there, it doesn't change the circuit. And now I see that C, D, and E are all 3 shorted out, dark. Nothing goes through them. Okay, and A and B are totally unaffected. They are on an independent path. Now, do you believe that? Well, let's find out. We can do the experiment. Okay. So I started out with the wire here and here. Now, watch what happened when I put that in there. A and B don't care. They stayed the same. F got brighter and these guys went dark. Now, if I move that over here, same, over there, same, over there, same. I can move this down here, same. Okay, so F got brighter. Why? Because I added a really good path to that right side, and F was an indicator for that right side.
Can you move that over to E, bottom part?
Oh, I sure can. Same. Anywhere along the wire. Whoa. Old man coming.
I understand the charge level. And using like the voltage with the current model, would you be able to explain why A and B are still?
Yes, I can. And that's the better way to think of it. Thank you for bringing that up. And that is that with the voltage model, any path from one side of the battery to the other has to add up to the 12 volts of the battery. And so if I go back to where it was here, if I take this path from the positive terminal of the battery through A and B and back, they've got to add up to 12. And there's no reason to expect this one to have more volts than that one. They're in series. And so that's going to be 6 and 6, regardless of whether this is connected there or whether it's connected there. Likewise, if I have it here, from here to here is 0 volts, because this wire is parallel to this path here. And so if it's 0 volts along that wire, it's got to be 0 volts along that path or 0 volts along that path. Okay. How we doing? Yes. They are completely independent of each other.
Why it's allowed that we can put a wire on one then put together? I feel like that makes them no longer.
Well, the definition of parallel across the battery was that I could find connections with nothing but wire from one side of the branch to the battery, and on the other side of the branch to the other side of the battery. And if I combine A and B, I can find a connection with nothing but wire to the positive terminal of the battery and nothing but wire to the negative terminal of the battery, whether that wire's there or not. Right? There's nothing but wire. That's a wire, that's a wire, that's a wire. Okay. If you put numbers in, let's say we arbitrarily define the voltage at the negative terminal of the battery to be 0 volts, then this would be 12 volts. And everywhere along a wire, we have no change in voltage. So that's going to be 12 volts, 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 that's going to be 12 volts. Along this wire, it's 12 volts, 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 12 volts. So now I see the voltage here is 12 volts, the voltage there is 12 volts. We don't care about the voltage, we care about the change in voltage. And the change in voltage from 12 to 12, 0.
You allow to move the wire any place between two different resistors? You just can't.
No, any place between, as long as you stay on a connecting wire, it doesn't matter. As long as you don't cross a bulb or a resistor or a switch or a battery. Or a capacitor, yeah. Let's put some capacitors in there.
What happens if you put the end of the wire between A and B?
Oh, yes. If you put the wire between A and B, now it becomes a very more complicated circuit and nothing is shorted out. But the brightnesses will change. You want to see how? Okay. You wanted to put it from here to here, right?
Yes.
Okay, so both sides are gonna change. Wait, what happened? Oh. That was at 6 volts and this was already at about 6 volts, and so it didn't change much. Yeah, that didn't have much effect on the circuit, but that's happenstance rather than physics.
Okay.
They were both at about the same voltage before we started.